Thank you, Fernando, Raul, all my friends here. I'm extremely proud of being part of the ISFGS since the very beginning, so 10 years, an incredible journey. And really, I mean, Fernando gave a presentation about all the statistics. It's absolutely impressive. Really, thank you. So, a little disclosure. It's 1 year. I also have a birthday to celebrate. It's just 1 year that we created a startup company in Fluorescence, so it is a relevant disclosure. It's called Astranice. I will show you what we do. And I also moved since 1 year in Geneva. And the motto of Geneva is Post tenebras lux, so the light after darkness. And I felt like, wow, that's really a cool place to be. Because obviously as surgeons, surgery is a job of the eyes, right, mostly. The eyes, the end of the brain, but it's a visual discipline. So unlike when you give a drug, you have to figure out the patterns of all the pathways. In surgery, we see what we do. And this classified the different type of enhancement, and seeing by transparency, the concept of virtual and augmented reality, seeing the microscopic with techniques like technologies like endomicroscopy or optical coherence tomography, and seeing the invisible. It comes to surgical optical imaging, which is fluorescence, of course, but not only. And we created 10 years ago the Spectra unit. So together with this gentleman, we started to think about how to really exploit, taking out the greatest advantage of those technologies. So we thought that it was great to have a chemist on board, an optical engineer, someone that can do hardware, and a software engineer. So hardware, software, and fluorophores. And I was lucky enough to attract big grants, and these are all my PhD students. The last two gentlemen, they are still there, sitting in Strasbourg while I'm supervising them from Geneva. And we did many things. So what we study is physical properties, so light tissue interactions, and they all occur simultaneously with a different degree. So you have the fluorescence, which is the change of the energetic status, but you also have reflection, diffraction, absorption, scattering, and all of these can be exploited to create images. So you have the exogenous information, which is fluorescence or autofluorescence, in which there is an energetic status change, delta, but you also have absorption, scattering, or other phenomena that can allow you also to quantify, utilizing a spectroscopy with a camera to quantify biological compounds like bile, water, fat, etc. And these are the endogenous imaging modalities that we have used, but I will all today talk mostly about exogenous fluorescence, just to give you a sense that this exists as well, and that there is the possibility to combine exogenous and endogenous, and I will show you something. So this is the assessment, one of my PhD students, the assessment of oxygenation. This is not perfusion. It's the level of oxygen, is STO2, that you evaluate by imaging on, for example, this is a colorectal resection. So we, in the unit, we were thinking about what we can do to improve. This is a great technology. It's clearly something that will change the way we do surgery. And so we started thinking about the limitations, so the problems. ICG, great molecule for some applications, so like for liver, for cholangiography, you cannot do better than that, but it has some limitations. It is a small molecule, so it diffuses. It has a biliary-only metabolism. It quenches. It's not targeted. And of course, all the questions about quantification. So we started taking all these problems one by one. I cannot make all show you everything, just some selected things. This is a European study, CAST, and I had the privilege to collaborate with Alice Vermeyer there, in which the concept is to use targeted fluorophores. This is the EM137, is an anti-CMET, to follow up, to improve the watch and wait approach in rectal cancer after neoadjuvant radiochemotherapy. If you have a disappearance of fluorescence, you can estimate that the cancer has been healed. So why to operate if the cancer is healed? Just follow up with molecular endoscopies. That's the contribution of my PhD student, in which basically the idea was, can we, rather than inject spray and allow directly during the endoscopy the dye to stain and target, And you can see that when there is no fluorescence, basically there is no cancer. If there is fluorescence, there can be cancer or not cancer, but when there is no fluorescence, there is no cancer. This is extremely fascinating and important. However, developing those dyes, this is drugs, so it follows a very hard regulatory pathway and very expensive. So we thought, why don't we use a different approach? So that 10 years of research that is leading to now a startup company. And we created a polymer that embeds a fluorophore, which has very nice properties. So NICE stands for near-infrared coating of equipment. So we use the polymer to stain, to coat surgical devices. So it is not a drug. It is 30 times brighter than ICG. If you see the peak there is the red peak at 800-something nanometers. And it does not photo-bleach at all. But the beginning of the story was a very academic concept. So we wanted to do two things. The robust augmented reality, so to do a perfect registration between a virtual and a real patient, and to introduce a standard. I will show you this. So we were the first to introduce the concept of robust augmented reality. You see, this is a gold fiducial coated with the NICE. So the idea was, let's bring in the same wood a 3D reconstruction of a CT scan and optical analysis. This is because there is a very precise relationship between the distance and the intensity. And this can be used to inform how to deform a model. So you see, this is a kidney. We planted some of these fiducials. And when you apply a deformation, also the virtual model will be deformed according to the change in the shape and the change in the intensity of the fluorescence imaging. And we did this in, of course, ex vivo, but also in vivo. And this is 2017. This has been the beginning and will be a very long-term project, because in the meantime, we thought, okay, but we can do a lot of things with this technology. Actually, we have identified something like 63 different clinical applications. For example, we can coat clips and to identify tumors rather than injecting or tattooing. And this is, for example, in the cadaver study, we did in the colon, we did in the stomach. It is extremely bright, and it's pretty nice, and it works exactly in the same wavelengths of all the available near-infrared 1 machines. It can be modified. It can also work in the near-infrared 2, so to achieve deeper penetration. So that's the clip. You can coat the ureteral catheter. It's true that this is rare, but when it happens, it's painful. Again, cadaver model with a D-Light P from Karl Storz. So we can do much better now. The sensitivity has improved, but you can see how nicely you can identify the catheter. And obviously, the idea is also to compete in terms of costs, because this is a very low-cost technology. And another example, the Foley catheter, the idea was to reduce the occurrence of urethral injuries during a TME. But actually now we're also thinking to use it for prostate resection, because you can see the neck of the urinary bladder very nicely. And then the fluorescence standard. This is extremely important. So we created a proprietary calibration card in which, thanks to the geometry, the difference in concentration, you can know the distance between the target and the camera. And not only, we measure with the spectral imaging, and actually we can quantify the different concentration in the different points. And this is extremely precise. We validated in this study basically, we achieved a correlation of 99% between the concentration and the reflectance, which is the physical property that is used to do imaging. Why this can matter? Because imagine I put again this image. You see there is a gradient in those fluorescence imaging. This is targeted molecular endoscopy, and obviously you can think, this is yet to be proven, but you can think that the difference in intensity can be related to the quantity of antigen that is expressed. So you can go and target precisely, imagine in a Barrett esophagus or whatever, if you can really quantify this difference in intensity. And these cards are for calibration between instruments, but also for intraoperative navigation. So we have two types of cards. One is just to calibrate instruments, and the other one is to literally during the procedure to understand and quantify during the procedure. So the very important point is, as said, is this distance intensity relationship. And so we studied this very, very deeply because we introduced this into a software that basically was my PhD work more than 10 years ago. And we created a concept. It's fluorescence-based enhanced reality, in which this is a time-dependent evaluation in which a heat map is created based on the speed of the signal to reach its maximum peak. And we validated this very deeply, very scientifically with mitochondrial respiration on biopsies of the bowel, with metabolomic profiling, and with capillary lactate. And this is the thing that we used also to validate in a clinical trial, in which we use this quantification method. You see the ICG has been injected. This is a devascularized sigmoid, and you will see that the ICG progressively goes also into the devascularized part. And actually, scientifically, we published this in a different paper that I'm not citing here. It can go up to 8 centimeters. So ICG can diffuse up to 8 centimeters. It's just that you don't see it, but if you get closer with your camera, you will see that as diffused largely. So you see, this is a time-dependent evaluation, so it's not influenced by the distance. And with this software, you can basically attribute what's the perfused area, what is not perfused, and then you will have a cut, a resection line that will be displayed, and according to what percentage you can visualize that. Literally, it can give you values, relative values, of course, about how perfused is that area. And you can see on the proximal resection, the surgeon had placed 2 clips. So the novelty of this study is that we measured the lactates in the human bowel. This has never been done before. And you see the surgeon that you see that there is residual fluorescence on the proximal resection, and the surgeon had put clips to decide, I will cut here, and the software was suggesting I will cut a couple of centimeters more proximal. And actually, when we measured the lactates, on the clinically chosen level, lactates were 6.3 millimoliter, and on the software prediction were 0.5. So in this trial, there were 27 cases, 5 leaks, and all of the 5 leaks could have been predicted. I don't say avoided, but at least predicted, all of the 5. So just to conclude, my last PhD, Gabriel, is working on another European project. It's named Concise. We developed a completely innovative method to do imaging, in which we combine exogenous and endogenous. In Geneva, I'm working with Domenico Della Volpe, is a professor of physics at the CERN and the University of Geneva. We are creating POSIX. What's POSIX? Is the first handheld and completely wireless gamma camera that can see technetium. So the idea, and if there are any breast surgeons that are interested, we want to start with breast surgery. We are looking for money, and it's really, really impressive. And yeah, so fluorescence imaging, I absolutely agree with the previous speaker, is here to stay. And it's a surgical precision tool. It has some limitations, so quantification and standardization, but there is a way to improve that. There is a limited depth of penetration. Also, this can be improved. I think that combos will make a big difference. So radio tracer and fluorophores, 3D virtual reality and fluorophores, endogenous imaging and fluorophores. I think the combo will improve the entire state of the art. And yeah, to again celebrate the 10th birthday of the society, I use the words of Marcel Proust. The real act of discovery is not finding new lands, but seeing them with different eyes. Thank you for your attention.